In this video we're going to talk about humans and the sky, how our perceptions of the sky have changed through time. And to start, we're going to imagine that the Earth is turning inside of another sphere called the celestial sphere. Now the celestial sphere, from our perspective, doesn't change. It's just all of the stars and planets and moons that we see in the sky, and we are turning inside of it. So it appears as if the celestial sphere is turning counterclockwise. The north pole of the celestial sphere is the star Polaris. Each night the stars and other objects appear to encircle Polaris in a counterclockwise motion. It's easy to picture this as an umbrella with Polaris as the center point of the umbrella. And they appear to move at the same rate that the Earth rotates, which is 15 degrees per hour. Now the position of stars never appears to change in the celestial sphere, but over weeks and months the position of planets do seem to change in relation to the background stars. So here we see Jupiter slowly moving through Gemini, through the constellation Cancer, and then making this loop-type motion. This is caused because both Earth and Jupiter have separate orbits, and so sometimes it seems like planets have a backward or retrograde motion. Now, ancient people saw the same things that we see, but they explained what they saw in the sky with stories that personified celestial objects as gods or story characters like Hercules. Early astronomers in Persia or Greece explained what they saw in the sky using a geocentric model of the solar system, which means that the Earth and not the Sun is at the center and everything else goes around the Earth. The most famous of these models was Ptolemy's geocentric solar system, with Earth at the center and complex orbits of other celestial objects that attempted to explain why we sometimes see that backwards retrograde motion in the sky. Modern astronomers, since Copernicus, explain what they see in the sky using a heliocentric model of the solar system, which means that the Sun is at the center. We also now know that stars are really big and really far apart. Copernicus's heliocentric model had the Sun at the center of the solar system, and celestial objects had simple circular orbits around the Sun. Today we can send cameras and people into space to watch Earth rotate and revolve. But how did people figure out Earth's motions before the age of space exploration? Well, there's two pieces of evidence for Earth's rotation. The first is that a pendulum in motion should swing back and forth, but over the course of a day it appears to change its direction. And this is because the Earth rotated underneath the swinging pendulum. The second is the Coriolis effect. Imagine a cannonball is shot from the equator toward the North Pole. While the cannonball was in the air, it would seem to turn and change direction. This is because the Earth rotated underneath the cannonball while it was in the air. Now, we're going to talk a lot about the Coriolis effect when we study global wind patterns and ocean currents, but for now all you need to know is that it's a piece of evidence for Earth's rotation. There are also two pieces of evidence for Earth's revolution around the Sun. The first is the seasonal changes in constellations. In the celestial sphere, there are 12 constellations that are aligned to the orbital plane of the Earth and the Sun. These are called the zodiac constellations. You can see in this diagram that as the Earth is orbiting around the Sun, if you could imagine a straight line from the Earth through the Sun, it would point at one of the zodiac constellations. So because you can't see these constellations throughout the year, that is evidence that the Earth is orbiting around the Sun. The second piece of evidence for Earth's revolution is the changing apparent diameter of the Sun. And when the Earth is closest to the Sun in its orbit, it's called perihelion, and the diameter of the Sun appears slightly bigger because the Earth is slightly closer to the Sun. And the other time of year, when we are on the other side of our orbit, the Earth is furthest from the Sun, and that's called aphelion, and the diameter of the Sun appears slightly smaller. You can see in this image there's a small difference where the image on the right is slightly bigger than the one on the left. And finally, it's important to remember the dates of aphelion and perihelion. Aphelion is July 2nd, and perihelion is January 2nd. Notice that we are closest to the sun in the middle of winter in the northern hemisphere, which is a further reminder that the seasons are caused by Earth's tilt and not by our distance to the sun.